Okay, nevertheless, so I included the figure on the right just to remind us about the mineral systems approach. And so we're going to be talking about individual deposit types. Um, and so some of these themes will come through. The image on the left is just because we like funny things. Um, and iridium is a PGE. So leave that one for your humor. So what are we going to learn in this lecture? So the book breaks things up into a whole variety of ore deposit types, and I just felt that it was too much to go into every single one of them. So I've highlighted the ones that we're going to focus in on in bold. So I will mention nickel cobalt laterite systems, just like one slide. I'm not going to talk about skarn systems because they're really sort of outgrowths of porphyry systems. But we will talk about mafic intrusion, although Bob has already introduced that. And we'll talk about IOCGs again, porphyry systems, volcanogenic massive sulfide deposits, SEDIC systems, MVT deposits. Decided not to talk about Broken Hill, even though it's a massive system. It's basically sits in the interface between SEDEX and VMS. We're going to talk about lithium as well. Okay. So, Chapter 5 organizes scarce critical minerals by their ore deposit type. And so we discussed mineral systems of abundant metals. That's what Bob's just talked about. And here are a limited number of economic elements in the deposits being, that doesn't actually make much sense. I guess what I'm saying here is that what I'm trying to say in that statement is that a lot of these systems that have abundant metals also have less abundant metals that are still critical. And scarce critical minerals have a much lower crustal abundance than the ones we've just talked about. So the deposits of scarce critical minerals may have many element components with a large number of combinations. And by that, I mean, a deposit. So if we think about a copper-rich volcanogenic massive sulfide deposit also has lots of zinc and lead and gold and cobalt and things like that. And equally, a volcanogenic massive sulfide deposit, which is dominated by zinc and lead, still can have lots of copper and gold and other critical elements. So deposits have different zoning and temperature variations from different deposit styles, which leads to greater elemental diversity, and that's what we're really interested in. And so we're really looking in this lecture at things like lithium, cobalt, nickel, copper, zinc, gallium, and lead, although the chapter also includes lanthanum, cerium, and praseodymium, the three lightest of the rare earth elements. But I think we'll talk about those with the rest of the rare earths in another lecture. And so these kinds of deposits where we get these scarce minerals are from a wide variety of tectonic settings. And so this is a plot which shows the log of the annual production in kilograms per year on the x-axis and the log crustal abundance in ppm on the y-axis. And what we can see here is that in pink are the rare, and yellow are the scarce, as we would call them in this book, and then in green are the more abundant things that Bob's just talked about. And what we can see is there's an interesting linear, quasi-linear relationship there between crustal abundances of metals and their annual production, which kind of makes sense. If they're more rare, they're harder to produce. So
Well,
yeah, go ahead.
So another way to think about this is look at rubidium. There's a lot more rubidium in the crust than is produced, right? And I guess that's because nobody really wants rubidium.
Right. It's not an essential it's not an essential or critical element. Yeah, I'm not even sure what rubidium is used for.
Yeah.
Whereas
look at something like, antimony. It's not very abundant. but it's quite a bit produced. I guess, that correlation line sort of, how you interpret the deviations from the correlation line is interesting.
Well, I
And
guess you would say that things to the right of the line are in high demand, irrespective of their crustal abundance.
yeah, and to the
To the
left,
left,
or something could be in high demand, but you just can't really get, it just doesn't concentrate. Maybe gallium. Oh no,
yeah,
gallium.
the rare earths are mostly left of that line too.
Yeah,
Yeah,
interesting.
yeah. Sorry, someone had a question. Addison.
Oh yeah, I was wondering about the carbon including fossil fuels versus what I think is just the carbon, which I'm assuming is just mostly graphite. So there's one to like the far right
Yeah,
and
yeah.
one
So
right in the line.
yes, I think you're right. Just the C alone would be graphite, and then the fossil fuels is way off to the right there. And really, what we're trying to do with the greening economy is bring that one off to the right and pull it back to the left, right?
Yes, we are.
Good luck with that.
Mhm.
Yeah. Okay, so here's the periodic table of elements, which you've seen. This is from the textbook, and so we're interested in the ones in, I've put a red box around scarce, so the ones in orange with crustal abundances are in the order of 10 to 100 parts per million. So again, copper, nickel, cobalt, zinc, gallium, lead, lanthanum, cerium, neodymium, lithium. Again, I'm not going to talk about the rare earths here. So we can think of deposits in this sort of spectrum, going from magmatic or orthomagmatic deposits on the left, all the way through to surface processes on the right. And so what we're going to do, we're going to step through these as we head down the temperature scale in the different deposit types. So Bob's already talked about magmatic deposits, but I will talk a little bit more about them. And so these are the nickel copper PGEs, the iron titanium vanadium ones. We can include diamonds into magmatic deposits, although I guess diamonds aren't critical minerals. I mean, they're used for a lot of industrial purposes as well as jewelry, but nevertheless, they're not critical. Okay, so mafic intrusion related nickel copper PGE systems. And so the diagram on the right is the oddball, which is the Sudbury igneous complex. And the town of Sudbury is right here. So it's a good thing the impact happened 1.86 billion years ago, because otherwise Sudbury wouldn't be there anymore. Um, it's really cool because just off to the east, there's another impact crater, which is 46 million years old,
Yeah,
called Wanapete, it's a lake, 140, 150 meter deep lake. So Sudbury is a nexus for impacts, I think. But anyway, what's really cool about this is we basically have all the way around the outer rim of the Sudbury igneous complex, we have a whole series of nickel copper deposits. Um, so it's a very nickel copper rich system. There's lots of PGEs that are extracted, but nickel and copper are the main commodities.
So
Anyway,
you contrast this with the Bushveld. The two of them are similar, except that um, Sudbury has nickel and it has copper. I guess Bushveld has nickel, but no copper, right?
no, the Bushveld has some copper and nickel, but the dominant economics are from the chromite and the PGEs, whereas in Sudbury it's the reverse. The dominant economics are nickel and copper.
Interesting.
Yeah, it's a nature of so Sudbury is not generated by partial melting of the from a deep mantle plume, right? Whereas the Bushveld igneous complex is. Sudbury was a very large impactor that created a huge melt sheet. So not a partial melt, but a complete melt. But the target rocks were quite different.
Hmm.
So, and that leads to different styles of mineralization. Now, that's not to say the mantle wasn't involved, but it's from the top down as opposed from the bottom up
Hmm.
and the Bushveld. So, as Bob said, magmatic ore deposits are also referred to as orthomagmatic deposits or cumulate deposits. And so they form within igneous rocks or at the margins of igneous rocks. And ore minerals crystallize by melts or were transported by melts.
Well, we had one example of something that might be an orthomagmatic deposit where its liquid immiscibility is possible, with the Karuna IOAs. But that's very controversial.
Yes.
Whereas there's general agreement that some of these orthomagmatics are cumulates.
Yeah. It wasn't that long ago that some people tried to argue that Sudbury was a diatreme, was from the bottom up, so an explosive volcanic product or edifice. But most probably 99.99% of the people would say no, it's an impactor now.
Yeah.
And it's interesting. In the book it calls it an astrobleem impact, implying a meteorite of some kind. But a former postdoc of mine suggests that it was a comet. So,
yeah.
Okay, so the book talks about three main types, but other people classify it into five main types. So astrobleem type. And what's interesting about Sudbury, the nickel-copper ratio is around 1. And Sudbury is the second largest nickel-producing mining camp in the world. Then we have komatiite volcanic flows and intrusions. So these are ultramafic intrusions and ultramafic lava flows, which we'll talk about, where the nickel-copper ratio is more than 10. And some examples include Alexo Mine in Ontario, the Thompson Nickel Belt in Manitoba, Kambalda and Agnew in Australia. Then we have rift and continental flood basalts and intrusions with a variety of nickel-copper ratios. And the Norilsk series of deposits in Russia is the largest nickel-producing site in the world, although I wonder where they're selling that into right now. Then we have gabbro and orthosite intrusions where nickel-copper ratios are more like 2 to 3. And Voisey's Bay in Labrador is a good example of that. Voisey's Bay is a very interesting deposit. It was found, so it's a nickel-copper PGE deposit. It was found because some people were out looking for diamonds and were in a helicopter and decided to land on some Gossan-looking rocks, some iron oxide-looking rocks. And they found Voisey's Bay, which is a huge deposit. So it was found by accident. And then we have PGE-rich layered intrusions, such as the Stillwater in Montana or the Bushveld in South Africa, and the other ones that Bob showed earlier. And so here's a map of mafic intrusion-related nickel-copper PGE deposits in the world. There's an awful lot of them, but there's only, the number of very large ones is more rare. And so the map that Bob showed is better representation of the large ones. And so here's the age distribution of the deposits. It looks very biased to the left, but we have to remember that the big bar on the left represents about, half of Earth history, more or less. And the next bar next to it is another approximately 2 billion years of Earth history, whereas, the next 3, but we go from the Paleozoic onwards, that's 540 million years of Earth history. So you have to keep that in mind, that this bar chart is a little misleading. Nevertheless, lots of deposits in the Archean and the Proterozoic. So magmatic nickel-copper systems generally contain between 10 and 100% sulfide minerals. They can be massive sulfide, they can be net textured, they can be disseminated, so dispersed throughout the rock. Major sulfide minerals include pyrrhotite, which is Fe1 minus XS, where X is between 0 and 0.1. And just as an interest, FeS, pure end member, is called troilite and is mostly found in meteorites, not on Earth. Only in rare cases can you get troilite on Earth. We can have penlandite, which is an iron nickel sulfide, and chalcopyrite, which is our main copper sulfide, which has lots of iron in it too. And then we get PGE, platinum, palladium, etc. So just some pictures of pentlandite and in the here in the brown, and then pentlandite and chalcopyrite over here on the other in the other figure. Okay, a very wordy slide. So most intrusions, Sudbury notwithstanding, are interpreted as being generated by partial melting of mantle peridotite, probably associated with, a lot of them associated with mantle plumes. Some Phanerozoic deposits may have been derived from partial melting of the metasomatized mantle lithosphere rather than the asthenosphere. So if we think about the composition of the Earth, we have the crust at the top, then the lithosphere, which is the rigid part of the mantle, and then the asthenosphere, which is the part of the mantle that behaves more plastically. And so we can alter that mantle lithosphere through a variety of processes, and maybe subduction is a good one, to metasomatize it, to add water, and that may be part of where Phanerozoic deposits come from. Most of these nickel copper PGE deposits are located at or within 100 kilometers of stable craton margins, and they form through a whole series of melt processes. So mantle partial melting, producing mafic to ultramafic magmas. Then we have to transport that partial melt into the crust. Then we have to saturate that magma in sulfide minerals to remove the metals as an immiscible sulfide liquid. And then we need to interact that sulfide liquid with more and more silicate melt, because we need to upgrade the metal content of that sulfide liquid by bringing more and more melt through. And I can talk about more of that next time. So I did change the PDF, so I've added a couple of things. Clint is going to put the updated version of the PDF on your site for you. But most nickel copper PGE intrusions are interpreted to have been generated by partial melting of mantle peridotite. Just a reminder that peridotite is olivine, orthopyroxene, and clinopyroxene rich mantle materials, with typically with an aluminum phase there, spinel, plagioclase, or garnet, depending on depth. Some Phanerozoic deposits, so younger ones, may have been derived from partial melting of metasomatized mantle lithosphere rather than asthenosphere. So the cartoon on the right, just to remind us that the lithosphere is the crust and the solid upper part of the mantle, whereas the asthenosphere is that part of the mantle that behaves more plastically. Okay. And then most deposits are located at or within 100 kilometers of a stable cratonic margin. And so we form these deposits through a series of a variety of melt processes. So we need to partially melt the mantle to produce mafic to ultramafic magmas. We then need to transport that partial melt into the crust. Now, mafic, ultramafic melts carrying lots of metals cannot carry much reduced sulfur, otherwise the metals would never make it up to form a deposit. So we need to add sulfur somewhere along the pathway to make an immiscible sulfide liquid. And then we need to interact that sulfide liquid with continuous re-injection of more melt in order to upgrade those sulfide minerals in the nickel, copper, and PGE minerals. And I'm not going to go into it, but for those that are interested, that's called the R factor. And the R factor is simply the ratio of how much melt went through the system divided by how much sulfide melt there is. And the R factors can be in hundreds to thousands. So we need lots of silicate liquid to produce a significant deposit of sulfide liquid. And then finally, we need to accumulate our metal-rich sulfide droplets to form an ore body. So we can go through that graphically. So we partially melt in the mantle, and we need a high degree of partial melting to release the nickel. And so this cartoon from Barnes and Lightfoot really represents, okay, we're going to leave behind olivine when we partially melt the mantle. We're going to partially melt things like chromite, orthopyroxene and clinopyroxene preferentially. So That's going to be our silicate melt, and we might have some sulfide droplets in there too. So we then have to transport that. So the melts are commonly interpreted to partial melting is commonly interpreted to have been associated with a mantle plume. So here we have a cartoon of a mantle plume with melts going off into various parts of the crust. In some cases, reaching the surface to produce volcanic rocks, and then we can form these deposits in a variety of settings within the crust, but typically close to where the crust is attenuated. So then we need to contaminate the magma to bring about sulfide saturation. And so in this cartoon, we've injected our partial melt, into crustal rocks, which are composed of previously existing sediments or previously existing igneous rocks. But in particular, the sediments can be sulfur rich. And so by interacting between the sulfur-rich sediments and the melt, we can introduce sulfur into that melt. And that external sulfur then is needed to segregate the sulfide minerals in order to make sulfide minerals. And we know this happens based on sulfur isotopes, which we talked about previously. So then we need to collect the metals in our sulfide liquid. So the sort of swirly symbols represents convection within the partial melt, and the gray dots represent our sulfide droplets, and those sulfide droplets accumulate nickel, copper, gold, silver, PGEs from the melt. So the more melt we can flush through the system, the more enriched those sulfide droplets will become in those metals.
Hey, Matt, is this one of the best examples that we have of the importance of liquid immiscibility in making ore deposits?
Oh, probably, yeah. Yeah.
Because it's
a great question.
You know, there's a lot of argument about whether or not silicate liquid immiscibility happens, but there's very little argument that it happens when you're looking at sulfide versus silicate melt. That seems to, and the difference in densities between the sulfide droplets and the silicate melt is tremendous. So these things just drop out like rain.
Yes, although it is interesting, there are different ideas of how we accumulate the metal-rich sulfides within the magma chamber to form the deposit. But nevertheless, this is the last cartoon here. So we have our silicate magma with sulfide droplets entrained in it, coming up a conduit, coming into some kind of magma chamber or something of that nature. And then because of, as Bob just said, the density contrast, the sulfide droplets can settle out. In some cases, they may settle out on the margins, become unstable, and form a slurry and sloosh down the side of the magma chamber. Again, people have different ideas of how these things happen. In some systems, we can get depressions within the walls of the magma chamber or the foot of the magma chamber called potholes, and they can accumulate in the potholes. So there's a variety of methods. Okay, so that's nickel copper PGEs in 12 slides. Very rapid fire. And so again, these are important deposits for our nickel, copper, and for our platinum group elements. And as we've mentioned before, the Bushveld is probably the premier example of accumulation of the platinum group elements. It's the largest repository of those metals on the planet.
John's got a question.
Excellent.
Yeah, I'm just not sure I understand the immiscibility. Is it just density differences? Is one polar and one's non-polar?
Great question. It's density. There's chemical contrast, whether it has to do with degree of polarity. I'm not 100% sure. Bob, do you know?
Well, this is an excellent question because we have talked about the fact that polar and non-polar melts don't like each other, and we all know vinegar and oil, but whether a sulfide liquid and a silicate liquid, I think if one of them is going to be polar, it's going to be the sulfide, because the silicates are not polar. They separate for chemical reasons that I'm sure are known, but are not known by me. So that's an example of an excellent question that deserves to be looked into more.
Yes,
and
an excellent topic for someone.
Yes, thank you. But I do think this is an interesting system, because in order to get the let's say the nickel to move with the melt, you've got to actually melt the sulfide phases in the mantle, and it's usually pentlandite, isn't? And so you got to have these high temperatures, and high temperatures are associated with early Earth history. That's probably why, even though that diagram is not showing the distribution per unit time, that most of these deposits are indeed old. But then once you get that nickel and copper and the PGEs mobilized with the melt, you've got to resaturate that melt in sulfur in order to get them to precipitate as sulfide liquids and settle. So it is an interesting chemical problem. So
yeah, and you need a fair degree of partial melting to get the nickel out of a lot of the olivine as well in the mantle. Yeah, hence the appeal to plumes. Okay, so very briefly, we'll have a quick look at komatiite-hosted nickel-copper PGE systems. It's one of the subvariants that are recognized in the textbook by Muller et al. So again, these are magmatic deposits, and one of the defining characteristics of komatiites, if you see the picture on the left at the bottom there, you can see that sort of linear fabric, and that is in the rock. So that's a polished slab of a rock, and that linear fabric is called spinifex texture, named after the type of grass, which is on the image on the right. That's spinifex grass. And basically what spinifex texture is rapid crystallization of olivine shooting along the C-axis, if I have that correct. And so you get these long olivine crystals from rapid crystallization.
Hey, I want to chime in. We see this texture in meteorites, in the in the olivines in chondrules, which are 1 millimeter melt droplets, and they also have this skeletal appearance, indicating very rapid cooling. So it's at a much smaller scale than these komatiites, but it's nevertheless another example of this distinctive morphology of quenched olivines.
So a true komatiite has spinifex textures, and it also has more than 18 weight percent MgO. So very magnesium rich, so requiring very large degrees of partial melting of the mantle. And generally, it's true that they have really not occurred much after the Archean. There's a few examples in the Paleoproterozoic, and some people argue there's a volcano in Central America. I forget the exact location. It's called Gorgona Island. It's just off Costa Rica, I think.
It's off Colombia, and Colombia, it's Cretaceous. Right. It's Cretaceous.
Yeah, about 80 million years. Yeah, and people argue whether it's a true komatiite or not, but nevertheless, interesting. So the mantle just hasn't been hot enough since the Archean to produce very many komatiites. Okay, so mineralization occurs in the intrusive components as well as the extrusive rocks, so the komatiite flows. Nickel's the main commodity, but also economic quantities of copper, cobalt, and PGE. And so this is a figure from the textbook showing the upper one shows a plan view of a komatiite flow. So because these are so hot and magnesium rich, they probably flowed very, very rapidly. And so you can see a sort of a flow like you might see from a Pahoehoe flow on Hawaii or something like that. And then in the bottom cartoon, we have a cross section showing the thermal interaction between the komatiitic liquid and the underlying rocks. And this is called thermomechanical erosion by the melt or by the lava of those underlying rocks. And that's probably where the melt gets its sulfur from. Okay, so they occur in Archean greenstone belts. Typical examples are in Western Australia, Zimbabwe. There's some great ones in Ontario and Quebec, Brazil, Finland, and Russia. So if you think about the geography of those areas, those are all areas with old stable cratons, i.e. that have lots of Archean rocks. So they're high degrees of partial melting, perhaps greater than 30 volume percent, associated with mantle plumes, and forms along conduits or flow pathways. That's where the ore deposits form. Any questions on komatiite deposits? Spectacular.
I just comment that these things, komatiites, because they're so hot, they have a very low viscosity. So they're thought to be able to flow farther than just about any other lava flow. Now, obviously, we don't have any komatiite lava flows that we can study, like we can study what's coming out of Hawaii or Iceland. But it's thought that Venus has got evidence of these very long channels, and some people have argued that these are komatiite flows on Venus. Clint's got his hand up.
Yeah, I forget if you mentioned, it seems like they're the only kind of lava that actually melts its own channel. Because modern lava doesn't. I mean, it'll run into something and it'll freeze, but komatiites were abundantly high.
Yep.
Well, they're the only ultramafic lava flow that we know of. So, okay. So where are we going next? My computer seems to have frozen. Try that. There we go. So very, very quickly, you're going to talk about nickel cobalt lateritic systems, and they're sort of off to the right hand side of things. But the book talks about them next, and I thought I would talk about them next too, because we're still talking about nickel and cobalt deposits, and fundamentally related to similar rock types. So here's a map of the nickel laterite deposits around the world. And nickel laterite deposits have been broken down into sort of three subtypes. Those that are mostly, the nickel is mostly associated with oxide minerals, which are the red dots. Those are mostly associated with what are called garnierite, which are garnierite sort of it's not a mineral per se, it's a class of talc-like minerals that are hydrous magnesium nickel silicates. And then the third, and those are in group blue dots, and the third type are associated with smectites, which are smectites of swelling clay, magnesium-rich swelling clay. And so currently 70% of the global production of nickel is from laterite deposits, and much to the annoyance of the miners in Sudbury, because the deposits in Indonesia now are so readily mined that it suppresses the nickel price and keeps Sudbury from being as economic as it otherwise would be. And so this is a sort of cartoon from a brand new book on supergene deposits. And so we have the first two, A and B, are sort of idealized cross sections of the oxide type. So you can see in the blue bar just to the right is the ore. And so you can see that in both cases, the ore is associated with iron and manganese oxides. And the underlying rocks are ultramafic rocks, hardsbergites and dunites. And so it's the weathering of these ultramafic rocks, which are rich in nickel and cobalt, and that weathering produces enrichment within the oxide zone. And so that's what gets mined. Panel C is the garnierite types, which again is sort of an alteration of serpentine minerals, which are in turn an alteration of olivine and pyroxene. And then the final one is the smectite. So where we have these magnesium-rich clays, which are enriched in nickel.
So if I could make a couple comments. Number one, this is a great example of a supergene ore deposit. You know, you hear these words supergene and hypogene, and I always had trouble, you know, locking in. But, you know, all of these processes are happening in response to the atmosphere and the hydrosphere interacting with hard rocks. And you notice that all of the underlying rocks are ultramafics, or they're enriched in the elements that are going to get weathered in this supergene process. So that's really sort of cool. And you know, the other thing is that these kinds of lateritic, you know, these are kind of soils. They vary. So if you've got the same process going on top of a granite, you're going to get a bauxite. And if you have the same kind of weathering going on top of an ultramafic rock, you might get a nickel-rich laterite. And so this is, you know, not only sort of a guide to exploration of the supergene deposits, it's also in these areas where you don't have good outcrops, an indication of what lies at depth that you might want to go after.
Because it's such deep weathering. And so you notice that's an excellent point, which I forgot to mention. You notice most of the deposits are in humid climates, so that we get deep weathering in warm, humid climates. Okay. And this is just a cartoon from the textbook, basically showing a similar thing to the previous cartoon, but it's sort of more stylized. So we have the oxide ore, where we have the nickel and cobalt associated with hematite and goethite, so our iron oxides, or including the manganese oxides, and then where we have it associated with clays or the saprolite zone, which is the weathered ultramafic zone, that's our clay and hydrous magnesium silicate ore.
So the nickel and cobalt, are they found in nuggets in this stuff, or are they distributed all through the ugly clay stuff?
Yes, ugly clay stuff. So they're associated, you know, they'll absorb to the iron oxides, although they'll get substituted into the clay minerals in the granierite.
Okay, cool.
All right, so now we're going to switch over to magmatic hydrothermal deposits. I'm going to start off with our IOCG. Now, Bob talked quite a bit about iron oxide apatite deposits and karuna-type deposits, and IOCG are sort of in that spectrum of deposits, and how you break them out depends if you're a lumper or a splitter.
Prepare to be confused.
Indeed. Okay, so IOCGs are really interesting because they're rich in copper, gold, uranium, and iron, obviously. But from an economic perspective, copper, gold, and uranium. They're structurally controlled, and they commonly contain intrusion-related breccias, speaking to the sort of magmatic hydrothermal aspects. They're characterized by an abundance of iron oxides associated with gold-rich and iron copper sulfide minerals. But what's really interesting about them is they're much less sulfur rich than, say, porphyry copper deposits, which we'll talk about subsequently. Some IOCGs are enriched in the light rare earth elements, and sodic alteration, that is sodium, assemblages are typical. There's not very many quartz veins or pervasive silicification that you find in porphyry copper systems associated with major intrusions. And the host rocks are volcano-sedimentary rocks that have typically been metamorphosed.
So that point about the lack of quartz veins suggest that there wasn't a lot of magmatic fluid. Is that the significance of the lack of quartz veins and pervasive silicification, or what is the significance?
That's a great question. I'm not sure what the answer is. It may be more a function of depth and boiling, I think, but I'm not sure.
Ah,
Great question.
cool.
So here's the distribution of IOCGs. So there's quite a few in Canada. There's some sort of young ones along the west side of Chile there into Peru. Lots in Australia, for example, including the Olympic Dam, which is a giant IOCG. There's
No,
Karuna.
the other thing, yeah, Karuna, even though we talked about Karuna as a Karuna type deposit, they're lumping it in with IOCGs. And you've got Southeast Missouri there, which is also, I imagine that's Pea Ridge. So, some people would say, oh yeah, these are all IOCGs. Other people go, no, 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 no. And the lumpers and splitters fight. So when I said prepare to be confused, that's why you're confused, not because you don't understand it, but because nobody understands it quite.
Well, and it's a good point. So when I was an undergrad or a grad student, there was no such thing as an IOCG. It's a relatively new class of ore deposit. So, it's sort of recognition as its own ore deposit type is, I'm not sure, I'm going to guess here, but maybe 20 years old, that sort of scale of time. So here's the chart on the bottom is distribution of zircons through time with some of the major supercontinent forming events. And on the upper side, in the open bars, we have the frequency of IOCGs through time. And then the gray bars represent the metal resources in megatons of iron oxide and copper. And so the reason I showed this is because there's this big pulse of IOCGs in the Mesoproterozoic. And as Bob's going to talk about in a subsequent lecture, interesting things didn't happen in the Mesoproterozoic. And so, we talked about how a lot of ore deposit types are fundamentally linked to plate tectonics. But the Mesoproterozoic is often called the boring billion because tectonically, well, lots of things happened tectonically, but plate tectonically, it was perhaps less significant, if that's a fair way of saying it, Bob.
Oh yeah, no, this is absolutely something I zeroed in on when I started getting involved in this controversy. It was like, okay, the geologists won't believe me, but maybe the economic people who are not interested in their papers, but they're more interested in finding new deposits will. Yeah. So that abundance of these things that IOCGs or Karunas or IOAs or whatever they are, they're concentrated in the Mesoproterozoic at a time when I think that the plate tectonics was something less important than other things. Now, the bottom graph, which is confusing, is all that is a plot of zircon ages. So that's basically that's an expression of when crust was being preserved. The more zircons are associated with granites, the more zircons, that means there must have been more granites or erosion of granites to put those zircons in the system. And it really doesn't have much to do with what we're showing on top, just to reduce that level of confusion. But yeah, this is a really interesting, that upper diagram is very interesting from a tectonic perspective.
Okay, so they're spatially and temporally associated with intrusive activity, and geochronological and isotope studies suggest involvement of primitive alkaline magmas. So some examples are the Carajas in Brazil and the giant Olympic Dam deposit in Australia. And there's lots of other evidence that they're associated with alkalic magmatism. They're volatile rich, fluoride rich, lots of brecciation with abundant potassic alteration, and the light rare earth element enrichment. So lots of potassium, lots of light rare earths are typical of alkalic magmas. And so they can be considered the deep-seated crustal scale processes rather than associated with the individual porphyritic intrusions, as a case with porphyry copper deposits. And so they're more, more related to deep crustal processes is basically what that's saying. And so here's sort of a cartoon, again, from the textbook. It's a little complicated cartoon, but we have this asthenosphere here. We have subcontinental lithospheric mantle here and here. And so we've generated a partial melt in the subcontinental lithosphere, ponded those magmas at the base of the crust, and then some of those magmas differentiate, come upwards and further up into the crust, and then depending on the IOCG, so some of them are written here. So Palabora is a deeper seated system compared to Olympic Dam, which is a much more shallow feature, and so forth. So you can see that there's a gradation of depths at which these IOCG deposits are interpreted to have formed.
But clearly hypogene. This is clearly a hypogene system.
Oh, definitely a hypogene system. Yes.
So probably as good of an example of a hypogene system as we'll get, right? As opposed to supergene.
As opposed to supergene. Although the nice thing about porphyry coppers, which we're going to get to next, is that the economics of porphyry coppers are fundamentally rooted in a hypogene plus the supergene to upgrade the hypogene, as we'll talk about.
Yeah.
Okay, so we're still on magmatic hydrothermal systems. So we're going to talk about porphyry copper gold moly systems. So these deposits are large and they're low to medium grade deposits. In other words, you have to move a lot of rock to get your metals out. A typical rich porphyry copper system might be 1% copper. That sort of thing would be a fairly rich one. So the hypogene or the primary ores are mainly structurally controlled, spatially and genetically related to felsic to intermediate porphyritic intrusions. That's why they're called porphyries. So in other words, porphyritic meaning they've got a large crystals in a finer grained matrix. So they're the largest and highest tonnage copper deposits globally, with the exception of the Olympic Dam, which is the IOCG we just talked about. And they're also significant sources of moly, gold, and silver, as well as rhenium, selenium, antimony, tellurium, and bismuth. So rhenium behaves a lot like moly, so it substitutes into molybdenite, which is a common sulfide mineral in porphyry systems, for example. Gold-rich porphyry copper deposits are typically associated with more intermediate intrusions rather than the felsic ones. And moly-rich porphyries are deeper and associated with more felsic intrusive rocks. And so porphyry copper deposits are interpreted to have formed in active arc environments. So the upper panel, we have oceanic subduction, so the subduction of an oceanic crust underneath oceanic crust, so we can make epithermal deposits, porphyry copper deposits. And then where we have subduction of oceanic crust under continental crust, again, we can make some nice large porphyry copper deposits there, such as in the Andes. Porphyry copper deposits are also interpreted to be post-collisional. So after we've collided a continent against or an island arc against a continent, we can reactivate deep structural systems and have more partial melting and produce subsequent porphyry copper deposits. So they're fundamentally linked to subduction, but can be post-subduction. And so here's
if I can just comment,
of course.
The most spectacular example I know of that is Iran, where Iran's
Mhm.
got this tremendous record of igneous activity due to the subduction of the Arabian plate, which started to collide with Eurasia about 25 million years ago. And that's when the porphyry coppers start to appear.
Mhm.
It's like an on-off switch. It's really quite interesting.
Yeah. Yeah. Here's a map of the location of porphyry copper deposits. So you can see the Pacific Ring of Fire, not to be confused with the other Ring of Fire, which is up in here in Ontario. So quite a ways away from the Pacific. And also on here, there's a lot of porphyry copper deposits associated with these post-subduction settings. So that Bob was just talking about. And in the big dots, we have the 10 largest porphyry copper deposits. So there's a couple in the United States, lots of them down in Chile. And then we have the largest gold-rich porphyry deposits. So Cadia in Australia, Grasberg in Indonesia, Oyu Tolgoi, which is also extremely copper-rich in Mongolia, and so forth. Oh, and Pebble. There's Pebble up there, which is a nice large porphyry system, which may never get mined. Lots of controversy around that deposit. But here's a cartoon, Jeremy Richards.
John's got his hand
Oh,
up.
go for it, John.
It really gets off the subject, but I was going to ask you about Pebble. Can they not mine that safely and protect the salmon?
Well, of course, that depends who you talk to, right? If
I
you
don't
talk to
know.
the
What
companies,
do you think? You're a scientist.
Yeah, I
That's
think
okay. I didn't know if you had an opinion
no,
or
I
not.
think no, it's a great question, and I'm only hesitating in because I have mixed feelings about it, right? On the one hand, I'm an environmentalist, and on the other hand, I do work for exploration companies. Um, so I would say that at the moment we've got enough resources of copper that there's is there an urgent need to mine Pebble? There's probably not an urgent need right now. There may be in 20, 30, or 40 years from now when maybe we can do things more responsibly. Maybe that's where I'm hedging my bets. How's that for an answer?
Great answer.
Yeah. I mean, I think, the same goes with mining the seafloor. Do we need to yet? Probably not. But it's important to know what resources is there in case we ever do need them. But just because something's there doesn't mean it has to be mined. That's my view. Okay, so this is a cartoon put together by Jeremy Richards, who had a sort of slightly different take on IOCGs versus porphyry deposits, in the sense that he sort of felt that they were similar systems, but the IOCGs represented a much more sulfur poor equivalent. So on the right-hand side of the diagram, if you split it in half, we have the alteration and mineralization styles of a typical porphyry system. And on the left-hand side, we have the typical IOCG. And the big difference you'll see there is on the left-hand side, we've got hematite and magnetite, so iron oxide rich parts, whereas on the right-hand side, the porphyry copper is dominated by pyrite and chalcopyrite. So lots of sulfides. And so a boring table, but I highlighted the bits that are important. Again, this is from Jeremy Richards' work. And so here we want to just see what the major metal associations are. So copper, moly, gold, and porphyry copper, and iron, copper, gold in the IOCGs. There's a lot of tin, tungsten, and silver in porphyries, whereas in IOCG, there's more uranium, rare earths, cobalt, and silver, high sulfides, low sulfides. Tectonic setting is subduction and post-subduction. IOCGs, post-subduction, back arc perhaps. And their age range, porphyry coppers are dominant in the Phanerozoic and very rare in the Precambrian. And IOCGs are dominant in the Mesoproterozoic, as we already discussed. And so this is an interesting plot from Jeremy Richards and Human. I can't remember his first name, but it's kind of a complicated diagram, but I just thought it was really interesting. So on the y-axis to the left, we have the seawater sulfate concentration, and that's this yellow bar here. So as we go through time from the great oxidation event around 2.4 billion all the way through to the present, the amount of seawater sulfate has drastically increased since the end of the Precambrian. The red line here represents the decrease in paleo heat production in the mantle. And then the two horizontal bars, the blue one represents where IOCG deposits are most typical, and then porphyry coppers are most typical in the Phanerozoic. So it's an interesting diagram. Yes, they may be similar systems, but there may be a fundamental reason related to the availability of sulfur as to why we get these different kinds of deposits, and plate tectonic style, perhaps.
Question from
Yes,
John.
Is there a reason for such a dramatic increase?
In seawater sulfate?
Yeah.
Yeah, because the oceans were much more reducing in the past, and then they become more oxidizing over time.
Yeah,
Thanks.
remember sulfate is SO4 double minus. So if you don't have a lot of oxygen running around, you're not gonna have a sulfite. It's gonna be sulfide.
Okay, gotcha.
And
Yep.
Clint's got to
Okay.
follow up.
Yeah, and one interesting thing about that is the influence of plant life, including algae, potentially on ore bodies, which is just like, oh, that's really interesting.
It is extremely interesting and probably a completely understudied. I mean, one could make the case that the influence of biology on many geological processes is understudied. Yeah.
My understudy will be studying it.
Well, especially on supergene deposits. So hypogene
Yeah.
deposits, not so important. Supergene deposits, probably very important.
Yeah, critters don't like 350, 400 degrees C fluids very much. So here's a cartoon. I probably won't read through all of this, but it sort of talks about how we make a porphyry copper deposit. So we have subduction, we dehydrate the subducting slab plus or minus sediments on top of it. So that's 1 or 2. And we get partial melt. When you add water to mantle, you lower its melting point. And so we get partial melting of the part of the mantle that overlies the subducting slab, which we typically call the mantle wedge. So those partial melts will then rise, pond at the base of the crust, and start fractionating and produce more felsic lavas, or felsic melts, sorry, not lavas, felsic melts. We get anatexis, or partial melting of the crust, related to these melts as well. And then ultimately we form the porphyry copper deposit at fairly shallow level, sort of 1 to 7 kilometers deep in the crust.
So another joker in this deck is the fact that we have VMS deposits forming at mid-ocean ridges, and they get subducted. So you could have VMSs going down and getting
That's true.
remobilized where it's got that dehydration of the oceanic crust. Because one of the questions is, where's all the copper coming from?
Yep.
And so it's either coming from the overriding plate, like in the lithosphere, or it's coming from the subducting plate. Because nobody questions the relationship between porphyry coppers and subduction. That's accepted. But it is interesting. Arizona's got so many copper deposits, and as compared to, say, California, and you're going, what's going on? So that would argue that it's the lithosphere of the overlying plate that's controlling. But interesting topic for someone. Yeah, and Clint's got another comment.
Yeah. And another joker in the deck for our friends in Canada is that there is a place called Anna, Texas, just up the road. All right, over to you.
Got a drum roll, please.
I thought that was a woman who lived in the South, Anna, Texas. Anyway. Okay. enough humor. This is just a photograph of Chuquicamata in Chile. I've not been down in the pit, but I have stood on the rim, and I can confirm it's a giant hole in the ground. It is massive. Each one of those, you see the sort of serrated side there on the western part. Those are benches over which these massive ore trucks drive around. Just, I mean, it's just an amazing thing. So it's the world's largest copper ore body. It's been mined since the 15th, 16th centuries by the Incas. It originally was an underground mine, and then it started being mined as an open pit in 1915. So they've taken out almost 2.5 billion tons of ore at around 1.5% copper, but something like 6.5 billion tons at least of 0.5% copper remains. So it is just a massive resource, which is why I said earlier, John, that I'm not sure Pebble's really all that urgently needed. Because Chuquicamata is just one of many large copper deposits in Chile. And then one of the really important things, which we keep talking about, is supergene processes. And so in this cartoon, below the water table, we have at the bottom, we have the hypogene ore. That is the primary ore that formed from the magmatic hydrothermal fluids through mixing with meteoric waters and various other things. In the next zone above, it's below the water table, but we call it the secondary sulfide enrichment zone. And that's because, let's go to the top. What happens at the top, if we expose hypogene sulfides at the top, they're interacting with oxygen and water. And so the sulfide minerals will get oxidized. Sulfur will get oxidized to sulfate. Copper gets oxidized to copper 2+, and they percolate down the water table, down to the water table. The sulfate either gets removed from the system by groundwater flow or forms secondary sulfate minerals. What happens to the copper is it can percolate down below the water table. Once it gets below the water table, it goes back to 1+ and enriches the primary copper sulfide minerals that are already there. So we take something like chalcopyrite, which has CuFeS2, and we make much more rich copper sulfide minerals by this upgrading process. Also, what happens in this oxidized zone, the copper can form secondary minerals, copper oxides, copper sulfates, copper chlorides, copper carbonates like malachite. And so we get this supergene oxide zone. It's called oxide zone, but they're not all oxides. And then we get the supergene enriched zone. And this process of supergene and hypogene enrichment, or supergene enrichment of hypogene ores, is what can make or break a porphyry copper deposit economically. Because you've taken the original hypogene and upgraded the metal content through these supergene processes. It's really cool. And so what you get at the top, what's left behind is mostly iron oxides because they're not soluble under oxidizing conditions. And so you get the leach cap, which is what's called in porphyry world, it's called a leach cap. In a VMS world, it's called a Gaussian. Same thing.
So this, just to add some cultural stuff, all over the U.S. Southwest, they love this silver cup coupled with malachite or azurite, the beautiful bluish green that people like for jewelry. And the reason for that is there's that malachite and azurite, that's all stuff near the surface. So if you see a place with a lot of azurite and malachite, there's probably a fair amount of hypogene copper sulfides somewhere underneath it, which is indeed the true for Arizona.
Mm-hmm. Yeah, the nice blue one. There's several blue copper minerals. One of them is chrysocolla. There's cuprite. Yeah. Okay, now we're going into sort of the high temperature hydrothermal realm, and we're going to talk about volcanogenic massive sulfide deposits. And so the cool thing about VMS that they occurred throughout much of geological history. There's some of the major sources of zinc, lead, and copper that we have on land. And we have modern analogs that are actively forming on the seafloor. And so the graphic shows you that we get, now I have to move this because it's being covered. So we get 22% of our zinc is mined from VMS deposits, about 6% of the copper, 10% of the lead, 9% of the silver, and some VMS systems are particularly gold rich. So they're a good source of gold as well. And so,
Matt,
yes, sir.
a question. What fraction of the mineral wealth of the Canadian Shield is VMS deposits, in your rough opinion?
Oh, that's a great question. Fraction, well,
Ballpark it.
ballpark it. 25%, 20%, something like that.
Oh,
It was.
it's not as important as I thought it was.
Well, gold is really important, and there are some gold-rich VMS, but gold's probably the major commodity coming out of Canada. And then we've got porphyry copper deposits on the west coast.
I was talking about the Canadian Shield.
Oh, and the shield itself, yeah. Maybe a little more then, but some of the deposits have shut down recently, so it's a lot. Brunswick
Right,
number
thanks.
12 was a major one. It's shut down, so.
Thanks.
Yeah. But it's a great question. I don't know the answer. Okay, so VMS deposits are typically strata-bound deposits that form in subaqueous environments. And so typically on the seafloor. And the fluids that are responsible are dominantly seawater, which gets modified by heat from a magma chamber or subvolcanic magmatic system and through water rock reactions. Although there's various people who feel more or less whether magmatic volatiles are actually important in giving the metal endowment of VMS deposits. So some people have modeled that you can get all the metals in a VMS through water rock interaction, through seawater interacting with the volcanic rocks through which it flows. And others have said that no, you need to have magmatic volatiles being degassed directly from the magma chamber. It's an interesting question. And so we can subdivide the VMS deposits into a number of different phases of mineralization. So we have mound structures, and mounds are typically formed by the coalescence of chimneys that fall over and get coalesced and upgraded by subsequent hydrothermal fluids flowing through that mound. We can have stratiform exhalative bodies, and we can have replacive bodies in the footwall, so vein and stockwork mineralization. And we'll see what that looks like.
Hey, Matt.
This is where, yes, sir.
2 points. Would you consider VMSs to be a supergene or hypogene?
Oh, definitely hypogene.
Okay, because it's happening at the surface, even though it's
Yes, but
very easy to link it to igneous. So and it's a very different kind of supergene than, say, lateritic supergene, right?
yeah. So, well, it's coming from below, so that's why we'd call it hypogene.
Oh, you'd call it hypogene.
I would call it hypogene, yeah, because it's being derived from below. If I said supergene, that was a mistake.
Oh, okay. So that's interesting because where it actually comes out of the sea and out of the sea floor, I would have thought anytime it interacts directly with the water, it'd be supergene. But we don't have to have this disagreement, except to let the students know that if they're confused, it's because their professors this is something their professors might argue about. So that's useful information. The other thing is it true that VMS deposits are the only place that we can actually physically watch an ore deposit forming?
Certainly that I know of, yeah. I mean, I suppose we can see the results of epithermal systems in places like Wairaki and New Zealand. So I guess it's not the only place, but it's certainly the best place. We can see epithermal systems. So
okay, cool.
Yeah.
Thanks.
Yeah. But no, we would call it hypogene because it's from below and it's not. Supergene is sort of mobilizing things from above. Put it that way.
Is
That's
there a
how I-
temperature difference? Is there a temperature limit below which you say, okay, this has to be hypogene? I'm sorry, temperature above which this has to be hypogene versus temperature below which this has to be supergene, or is that too simple-minded?
I think it's more a question of what's the source of the metals. And if the metals are coming from a fluid from below, it's hypogene. So that's a primary precipitation process. Whereas coming supergene is a secondary process.
Gotcha. Thanks.
Yeah. Okay, global distribution of VMS deposits around the world. So yes, there are an awful lot in Canada. Lots in Australia, lots in Scandinavia, and on the west coast of North America.
Interesting to see some in the Appalachians as well.
Indeed, indeed. There's quite a few deposits in the Appalachians where people argue about whether they're VMS or not. Because particularly in the Grenville province, which are rocks around 1 billion years or so, they're so deeply eroded and metamorphosed that it's hard to tell what they used to be. Yeah. And there's a map showing where we see modern examples on the seafloor. And so you can sort of break it down into two broad areas. One is on the mid-ocean ridges, so the East Pacific Rise. There's
Hand
lots
up
of
from-
known. What's
Hand
that?
up from John.
Yeah, John.
Yeah, I apologize. I get off on the side and all these things, but I see all these deposits in Japan. I don't think of them as mining anything. Is that just because they're so environmentally conscious that they don't mine?
No, there used to be mining in Japan. There's some really interesting VMS deposits in Japan. In fact, there are the Kuroko district, the Beshi district. So these are districts of Japan where traditionally mining happened.
Okay.
There's still some mineral exploration going on in Japan. At least there was when I was there some years ago, and visited a couple of these deposits. So, yeah. Now here, most of the stuff is south of Japan, along the Mariana Izubonin Arc, or the Izubonin Mariana Arc, I should say. So we have hydrothermal systems which reflect the process by which VMS deposits form. We find them along the arcs and back arcs. So in Izubonin, the north of New Zealand on the Tonga Kermadec Trench arc, sorry. And then we also find them on mid-ocean ridges. And as Bob alluded to earlier, the fate of a mid-ocean ridge is typically get subducted. So our best analog for ancient systems on land is probably those associated with arcs and back arcs. So where do we find VMS deposits? We find them in failed rifts. We find them in island arcs, rifted arcs, in back arc spreading, maybe in the fore arc and at mid-ocean ridge spreading centers. And then on continental systems, again, in the back arc or in the back arc. Fundamentally, what we need is heat and seawater.
So I'm going to ask you a question that if you ask it of me, I won't be able to answer it. But
Okay.
my question to you is, what's the closest VMS to Queen's University?
The closest VMS to Queen's University is probably just up in the Abitibi. So maybe 8-hour, 9-hour drive away.
Yeah, and I don't know where the nearest one is to Dallas.
Ooh, no. Well, you could argue the Guaymas Basin, there's some actively farming in the Guaymas Basin.
Oh, yeah,
That's not
yeah.
that far away. Yeah. So this is a chart of the size of VMS deposits in millions of metric tons, and then the numbers of deposits. And you can see it's very skewed to smaller deposits. The sort of the largest ones are in the sort of a few 100 million ton range. And what's indicated on there is Windy Craggy. Windy Craggy's in Canada. It's a giant copper-rich and cobalt-rich VMS. It's called a Beshi type because it's similar to the kinds that are formed in the Beshi district in Japan. It'll never be mined because it was going to go into production, and then some controversy about where it is. You'd have to travel through American waters to get the ore out because of the Alaskan Panhandle, and Al Gore got involved, and various environmental groups in Canada got involved, and so eventually it was turned into a national park. But it's a massive system. Slightly smaller, the Kid Creek and Brunswick number 12 deposits. Kid Creek's still going. Brunswick 12 is shut down. I've been underground at Brunswick 12 at the 1,100-meter depth. So it's pretty humbling to be in a small tunnel and knowing there's a kilometer of rock above your head. And then here we have the average ancient sulfide deposit is sort of around 10 million-ish tons. And the typical seafloor one is much smaller. Now, having said that, there are a few examples on the modern seafloor which are much bigger, but generally speaking, the modern seafloor ones are pretty small. So either something's fundamentally different, or we just haven't explored very well. And with this modern seafloor, we can see the seafloor. We don't have a lot of control over what's happening at depth. So there hasn't been very much drilling. And so it's just a cartoon. At the top, there's an image of tube worms, which are characteristic of VMS seafloor systems. So these very strange critters that fundamentally the entire ecosystem is based on chemosynthesis of hydrogen sulfide rather than photosynthesis. And over here is a plume of what's called a black smoker. So this is a sulfide chimney here, venting out this black smoke, which is mainly iron oxides and iron sulfide precipitates. And then the cartoons basically show how these systems look in cross-section. So these fundamentally form on the seafloor. Yeah.
Quick question. These organisms, their bodies are rich in carbon, and something I just wonder, is there any mineralization of the organisms, kind of like in a uranium, when uranium encounters wood? I understand uranium likes to join together with carbon. So
no, but not to my knowledge, but they get replaced by sulfides in the ancient rock record. So what's really cool is these tube worms, we find them in all the oceans. They don't all look like that. Some of them look more like spaghetti, but they're tube worms. You can find them on dead whales. You can find them around cold seeps, anywhere where there's a source of hydrogen sulfide. But you can find them in the ancient rock record. So if you go to VMS deposits in the Urals, which are a few 100 million years old, there are casts, I guess, of tube worms, which are now sulfide minerals.
yeah, it's interesting.
Yeah, so these things have been around for a long time. Okay, we're running out of time. Okay, so now we're going to go to low temperature hydrothermal systems, and we're going to talk about SEDEX and MVT deposits. So SEDEX deposits, what SEDEX stands for is, and I should have said it, I didn't, I apologize. It stands for sedimentary exhalative. So VMS deposits, let's go back to here. But fundamentally, what happens in VMS is we have these chimneys at the seafloor venting hot fluids that interact with seawater, and we get these chimneys, and these are formed of massive sulfide minerals, things like chalcopyrite and sphalerite and pyrite. And that then they fall and they coalesce to form these mounds on the seafloor. SEDEX deposits, and these are fundamentally linked in volcanic rocks. So SEDEX deposits were originally thought to be similar kinds of systems that vented at the seafloor, but in a sedimentary basin rather than a volcanic basin. Now, they're sometimes referred to as clastic dominated because there's no actual requirement that they vent at the seafloor. In other words, more and more research has shown that a lot of the mineralization might happen in the subsurface, not venting at the seafloor. Nevertheless, we can call them SEDEX deposits. And so they're part of a spectrum between these kinds of deposits, MVT deposits, and Irish type deposits, which we're not going to talk about Irish type deposit, but we will talk about MVTs. Just think of Irish type as being a hybrid. And so these mineral systems contain mostly lead and zinc, some copper, selenium, cadmium, indium, and germanium. So these are all essential metals, right? These are critical minerals. The mineralogy is fairly simple. The sulfide minerals are dominated by pyrite, sphalerite, and galena. So the ores of iron, sphalerite, and galena and lead. Sorry, the ores of iron, zinc, and lead. They're typically laterally zoned and laminated, and you can follow these laminations for lots and lots of kilometers. And they're bedding parallel sulfide minerals within organic rich shales and siltstones. So there may be a fundamental link there with organic rich rocks. So the plot on the left just shows the data is a little old now, but it probably hasn't changed very much, showing where we get zinc from. So in terms of zinc reserves, we can see VMS is around 30%, SEDEX is around 40%. In terms of resources, SEDEX dominates zinc resources. And in terms of production, well, VMS and SEDEX are roughly co-equal. I think, yeah, roughly co-equal. Okay. On the right-hand side, we have the upper plot shows the resources in millions of tons versus combined lead and zinc in weight percent. And basically what it's showing is that there's Canadian deposits and worldwide deposits. We can get some pretty massive ones, so super giant ones. And then the bottom plot just shows the grade versus the tonnage. So how many millions of tons there are of ore, of metal. And you can see Broken Hill, which is one in Australia, is a supergiant deposit. Okay. So this is what I was talking about before. So we have a continuum between SEDEX, MVT, and we can lump in VMS. On this plot, it's called VSHMS, volcanic sediment hosted massive sulfide, but that's our VMS deposits over here. So the Bathurst Camp, which is a large one in Canada, which shut down recently. So SEDEX deposits are characterized by moderate temperatures, sort of 180 to 250 degrees C. MVTs, which we'll come to, are slightly lower temperature, less than 200, and VMS typically more than 300 or more. Okay. An Irish type are kind of a hybrid between SEDEX and MVT.
Okay, I got a comment here because
Yeah.
The SEDEX MVT Irish type continuum is confusing.
Mm-hmm.
And so I've been struggling with this because we were writing a paper that finally got accepted. Yes. And we were struggling with this. It was about these kinds of deposits in Iran.
Yes.
And so we were, okay, what's the difference between SEDEX, Irish type, and NVT? So what I could figure out, and I might be wrong, is that Irish type are a SEDEX or an MVT that are associated with volcanic igneous rocks.
Correct.
Right? Whereas SEDEX and MVT do not. They're not associated with any such things.
Well,
now, well, to a certain extent.
yes.
SEDEX is associated with shales, whereas MVT is associated with carbonates. So typically, that seemed to me to be a subtle distinction that's causing confusion, whereas all three of these things are really similar. I mean, is that a fair statement?
Well, so SEDEX are contemporaneous with deposition, basically, right? So they form at or at the seafloor or in the subsurface, right? So give or take contemporaneous with sedimentation.
Mm-hmm.
MVTs, the mineralization can be much later.
Okay.
Right. Now, some SEDEX, like there's the giant Sullivan deposit in Canada, which is no longer mined, but it has lots of igneous rocks in the footwall. So, people like to say SEDEX has no mafic rocks, but that's not strictly true. What is true is people haven't actually figured what the causal or genetic relationship is between magmatic rocks and SEDEX deposits. So
part of it is the heat, right?
It's the heat engine
to set up a hydrothermal system.
That's right. That's right. And so in Irish type, they didn't used to think there was magmatic rocks, but then they drilled deeper and they found them. And,
Oh, okay.
So they're there.
Yeah.
Yeah.
So, thanks.
Yeah. So here's the SEDEX deposits globally. And Broken Hill, which is the giant one in Australia. I've had a student work on ones up here in Howard's Pass. There's the Sullivan one I just mentioned. Sullivan was an interesting one because they backfilled or at least they backfilled some of the adits with pyrrhotite, which is an iron sulfide, which is highly exothermic reaction when it oxidizes. And so there was an underground fire for decades. Couldn't put it out because it could shut off the access of oxygen, being self-sustaining. Not the only case where that's happened. Anyway, so you can see where they're associated with sedimentary basins primarily. And here they are through time. So again, there's a bunch in the boring billion, right? And then a bunch in the Phanerozoic. And so they're associated with sedimentary basins, controlled by subsidence and related to failed intercontinental rifts or epicratonic rifts. And so there's a couple of cartoons on the right-hand side. So the bottom panel is the one that's most commonly seen, where we have rifting associated with alkalic volcanism. So in the Selwyn Basin in the Yukon, that my student worked on the volcanic rocks that may or may not be related to SEDEX mineralization. And so they're commonly bounded by faults, and that's probably localizing the fluids as well. And so we can have what are called vent complex SEDEX deposits. So we have a feeder zone, so the sulfides are more massive, or that we have bedded sulfides where things are a lot more laminated. And if they do vent at the seafloor, it's possible that the very long extents of the bedded sulfides is related to this exhalation on the seafloor. The bottom panel just postulates that, so some models have SEDEX deposits requiring a sulfidic bottom water. So you can see there's a change from O2 in the upper water to H2S in the bottom water. And then these fluids are quite saline. So as they cool, they become dense and form a brine pool and make bedded sulfides. That's another model for formation. So you can see their salinity is roughly 10 to 30 weight% sodium chloride. And for reference, seawater is 3.5%.
So these brine deposits in the middle of the Red Sea, you would call them SEDEX deposits in formation?
That's a great question. Is SEDEX, are the Red Sea SEDEX or VMS or somewhere in between?
Yeah, they're but basically evaporites and
they've got evaporites.
Dense fluids have got a lot to do with them.
That's correct. That's correct. Whereas VMS are typically have salinities more around seawater. And so this is sort of the classic model that Wayne Goodfellow and John Lydon put together some years ago. And again, you can see the relationship there to magmatism. So the sill complex would be characteristic of the Sullivan deposit, for example. There's evaporites in the footwall. It's where we get some of the salinity. Wayne would argue we needed an anoxic bottom water to give the source of the sulfide to make the sulfide minerals. But you can see it's fundamentally related to sediments, rifting, and ingress of seawater which picks up the metals and brings them up to form at the seafloor or near the seafloor.
Are you going to cover Mississippi Valley type in this?
Yep, that's next.
Because that's kind of a slightly different story, isn't it?
Yep, so here's MVTs, Mississippi Valley types. So while our SEDEX tend to be found in clastic sedimentary rocks, although they can have carbonates in them, MVTs tend to be hosted in platformal carbonate rocks. But as I said before, they're part of the continuum with SEDEX. They're dominated by galena and sphalerite, and commonly have accessory barite, which is barium sulfate, and fluorite that forms epigenetically. In other words, the mineralization tends to happen sometime, and in some cases significantly long after the rocks were formed. So in terms of critical minerals, lots of lead. Well, that's not really critical, I guess, but zinc and gallium and galenium. Gallium and germanium, not galenium. Sorry, I've been talking too long. Gallium and germanium are found in the sphalerite. And they form from relatively low temperature fluids, sort of 150 to 200 degrees C fluids. And they tend to be hypersaline. So as saline or more saline than SEDEX deposits. So here's a model of where they form. So we have these platformal carbonates up here, dollostones. So we form the MVTs up in here. Then we can get their SEDEX sort of down in the deeper parts of the basin. Okay, so that's sort of the sort of spatial and genetic relationships between the two. So again, we need faults to transmit our fluids, but we're forming our MVTs primarily within the carbonate rocks. And here's just some pictures of what so you can get these sort of, what's the word I want? Coliform textures of sphalerite, or there's a very large crystal of sphalerite down in the lower one. And on the left, we have, again, production and resources in megatons, so millions of tons, lead plus zinc on the y-axis, just showing some of the large deposits in Canada. Pine Point is no longer being mined, but and Polaris were historic producers, very large deposits. Anyway, just showing some of the relationship between how big these deposits are. And you can see they're very metal rich, sort of averaging around 10% lead plus zinc. Whereas when I talked about the porphyry copper deposits, I mentioned that a good porphyry copper deposit is maybe 1% copper. And so the diagram on the right is for one of the MVT deposit in Canada, the Rob Lake deposit, and just showing that, again, it's sort of a replacement. So we've got the carbonate rocks, and then filling in space within the carbonate rocks, or karst sort of voids within the carbonate rocks. Hydrothermal fluids come up and deposit that material when they go through some change. So the hydrothermal fluids have to change their character by cooling, by mixing with other fluids, or by redox changes, by intersecting with organic rich sediments and that sort of thing. So they're fundamentally.
What's funny about the Mississippi Valley type is you're going, okay, this must be down in Mississippi or somewhere, but it's not. These things are found in northeastern Oklahoma, southeastern Kansas, and southwestern Missouri, maybe a little bit in Arkansas, where they've created a huge environmental, century of mining, and then that leaves these open shafts, and you get a lot of water, and then acid mine drainage. So it's been a really interesting story. But the name Mississippi Valley type, it's like, it should be called tri-state, right? Because of course, no one knows where Oklahoma, Kansas, and Missouri are outside of the United States. So maybe that's why they went to MVT. But isn't that true? They're really not anywhere near the Mississippi River.
I think there's some in the Mississippi Valley. Let's go back to I guess it's not a very good map, is it?
Yeah.
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 Well, there's some in there.
Yeah, okay.
Yeah.
I may stand corrected.
Yeah. Yeah, but the reason the acid drainage is because there's so much pyrite. Yeah. So when you oxidize pyrite, you get iron, and when you oxidize iron, you get acid.
You don't get it from oxidized galena and sphalerite?
No, because well, for sphalerite a little bit, because there's a little bit of iron. The main acid producing reaction is not it's not the oxidation of sulfide to sulfate, right? People think, oh, sulfate means sulfuric acid, but that's not really true. The main acid producing reaction is the oxidation of ferrous iron to ferric iron, so Fe2 plus to Fe3 plus.
Oh,
Fe3 plus is unstable, so it grabs hydroxides to form an iron oxyhydroxide, and that liberates acid.
oh, okay. Thanks.
Yeah.
Did not know that.
Yeah. So galena is not an acid producing oxidation reaction now. And so here's a plot of the MVT deposits through time. And what we see here is so the yellow bars are the host rocks. So we can see the host rocks are sort of Cambrian, Devonian, Silurian, Ordovician to the Cambrian and Precambrian. But the age of mineralization based on paleomagnetic or radiometric dating are Paleozoic and Mesozoic for the most part. So you can see that there's a significant time gap in some cases between when the rocks formed and when mineralization occurred. And then finally, I've been talking for a long time. The book talks about lithium deposits, and lithium is lots of people are running around the world trying to find lithium right now. Although I think we talked about there's other battery technologies being developed, and certainly in the lab, and whether they come to production is a good question. But for example, sodium ion batteries are being investigated and have some advantages over lithium, not least of which is the fact that sodium's a lot more common than lithium. So how much longer lithium will be a major driver of mineral exploration is a good question. But we have two major sources. So we have pegmatites. So pegmatites are these intrusive rocks. So they're magmatic rocks with very large crystals. And sorry, I just got to move this out of the way. Anyway,
we don't see it.
No, you don't see it. So you can read my text. I can't read it.
Yeah.
So significant lithium, beryllium, niobium, tantalum, cesium. These are things that are common in pegmatites. And then we also have evaporate-hosted brines. And I should say you could argue there's a third kind which people are thinking about, which is brines associated with oil fields. So when you drill for oil, you usually produce brine. And so people are considering whether they could extract lithium from oil field brines, which would be interesting.
I should comment that one of our UTD faculty members is very interested in evaporite-hosted brines in the Atacama. So I think she's down. Christina's down there now. Madison had a question
from Madison.
Yeah, I was just wondering if you guys if there's any like papers or talks you can refer me to that are looking at getting lithium from oil brines.
Yeah, I probably could. So this is Madison.
Yeah.
I'll have to look, but I reviewed some proposals a couple of years ago. They were seeking millions of dollars to try and research this. So on lithium from, I'm just making a note here.
Thank you.
Brines. Okay. Okay. So let's move on. So a boring table, but this shows some of the big deposits in terms of the pegmatite hosted deposits. So there's some very large ones in Australia. Greenbushes is more than 157 million tons at 2.2% lithium oxide. The main mineral is spodumene, which is a lithium silicate. Let's see. The Congo has the Manono deposit, which is 400 million tons at 1.6% lithium. There's a large one in Canada, which is not on here, called Tanko. But there's a couple other ones in Canada, and there's a newly discovered one in Canada whose name escapes me off the top of my head, which is in Quebec. So this is just to give you a sense of the size of the deposits. They're very large deposits at, reasonable percentages of lithium oxide. And spodumene is sort of the main mineral that gets mined. Now, these deposits are also good sources of other critical metals, as I said earlier, like tantalum and niobium and beryllium and things like that. So this is a plot which shows pegmatites in red. So the red bars represent the pegmatites. The gray bars represent granites. And then the colored bars represent different what's the word I want? Amalgamation of continents. Supercontinents. Thank you. Supercontinents just escaped me for some reason. And then the red star here, I forget which one that is, but anyway, that's a supergiant pegmatite deposit. So some of the peaks in pegmatite formation are highlighted by the different ages. Just showing that they're quite common through time, associated with granite formation. And here's what a pegmatite might look like. So you can see here's a large crystal of spodumene, and with a scale here. But if anybody's been to the Harding pegmatite in New Mexico, I used to take my students there when I taught at UT Dallas, and we'd map the pegmatite. And spodumene are on a scale of meters long.
It's gorgeous. It is purple all over the place.
Yes, that's the lepidolite, is the purple, which is a lithium mica. And then there's rose quartz as well. Yeah. So as granites crystallize, granitic melts crystallize, we get the incompatible elements. That is, the things that don't want to go into the crystals. They want to stay in the melt. And that includes many of the critical elements that we've been talking about in this course. So they want to stay in the melt. And those melts become rich in fluids like water, fluorine, chlorine, and so forth. And then these hydrous residual liquids get injected up fractures into the crust in the country rock, and they cool. So pegmatites go against the rule of big crystals means slow cooling. Pegmatites cool quite rapidly, yet make very big crystals because they're so fluid and they have relatively few sites of nucleation. So this is just a feldspar crystal in a pegmatite and a quartz surrounded by quartz. There's a hammer for scale. This is in Llano Uplift in Texas. And here's some of those spodumenes from the Harding pegmatite on the scale of meters long. There's a little mine there. When it gets really hot, that's where all the students hide, is inside the mine. And then finally, evaporates. So up in the high Andes, Chile and Peru and Bolivia, we have these large ponds of brines that they evaporate to extract the lithium. And that's all I really want to say about brine lithium deposits, because that's about all I know about them.